Hello guys, and welcome to Logic Gate video number 3. So this time I'm going to tackle the big one, the ALU. I already explained a bit in detail this adder complex right here. So now for the rest of the ALU. I already explained it a little bit. So basically, if you've been paying attention, then you know what an OR gate does, you know what an AND gate does. So this AND gate in particular basically just compares the output of B1 and A1. These are all going to be inputs like I have in the actual chip. Here's A1, here's B1. So it's going to do an AND operation on those, and then it's going to do another AND operation to check if the AND switch is flipped. So if this bit and this bit are on, then it will output that bitwise AND operation. So yeah. And then there's the OR operation. So, and I don't have like a checker to see if like more than one are flipped. I do that down here. I take care of all of the flippy stuff down here in the actual CPU and stuff. So yeah, actually zoom out a little bit. So if like the OR values, again, the buffers and the ORs and stuff. And here I have a bunch of NOT gates that are okay, so yeah, the buffers and the ORs and stuff. So if I put this on, then now that's on. Yay. So the way I have this is that the NOR, all the NOR is just basically a NOT gate attached to OR, and I have 4 of those for 4 bits and stuff, and then I have another set of AND gates for the NOR thing, and that of course goes to all the light bulbs. You see the OR gates here. Those are just to catch all these inputs, because you can't make 2 wires go to an output for some or an input. You cannot, 2 same wires cannot go into any one input. So if I try to link this to that, and then I tried to like link this to that too, it's not going to happen. You can't do it. So you need an OR gate to catch all of those. You know, in real life you could do that, but just for the sake of this program. And it's probably better to feed them into an OR gate anyway. We'll put diodes. So, yeah, that's that. Anyway, so here's an OR gate and stuff. Well, right, I was on NOR and stuff, and then add. So basically, just another set of buffers for the carry value. I have a carry value. Carries down here. It's only enabled for the add, since that's the only function that uses it, and a 1 over 2 over 3 over 4, and this is just the adder that you see right here. I tried to explain it in the last video. Here. Oh, I don't think I finished explaining that. So you saw in the last video that what these do. So basically, this is just a half adder, so if one of these are on, then it's going to turn on. But if both of them are on, then it's going to do a carry value. And that carry value is going to resonate into 1. Because you saw the demo for the full adder, it's just going to output another 1. So, I mean, if I add a various number in here, so let's add F to, and then let's add 1 to F, which is 15, so I'm going to be having 16. So then that's going to output a 16, which is the 5th bit. So if you have 5 bits, then the 5th bit is just going to be 16. So if I have 5 of those, 1, 2, 3, 4, 5, and I turn this on, 0, 0, 0, 0, 1 is going to be 50. I mean 16 in binary. So that's going to be a 16 because I'm having 15 and I'm adding 1 to it. Or if I have 15 and I have 15 and I like subtract 15 from it, then 15 subtracted from 15. So basically the algorithm for subtracting numbers is, so you have 4 bits, so let's say this is 5. So basically you invert the bits and you add 1 to the now inverted bits. So if I subtract 5 from 5, then that's going to give me 0. The carry value is assumed to be ignored in subtraction. So, yeah, that's the basics of adding. And then just a little bit on decoding. So basically just decoding is turning a binary output into a decimal output. Not really a decimal output. If it were really a decimal output, then this would be like some sort of digit thing. This is actually a hexadecimal digit, but I mean it can do decimal too if you just configure it right way. So this is going to turn it into basically just a decimal output from 0 to 7. 7 and 0. And this is, yeah, I mean, I guess you can follow the logic here, sort of. Maybe. So basically for 0, it's on unless any of these are on, and that if any of these are on, then it's going to not that, and then the 0 is going to go off. If this is on, if 1 is on, then 2 or 3 can't be on. So, but it's going to invert that in 1, and then you can just count like 2, 3,